Welcome, class. Once again, we will be looking at a video while you work through some problems that will prepare you for an assignment we'll be working on in a few minutes. Please begin on the warm-up problems shown below. You should use the warm-up paper you have. If you've misplaced it, then get a sheet of paper. Pause the video now and let students work on this for 5 minutes, and then we'll come back and discuss. Now that you've had time to complete the warm-up problems, let's remember how we do these. I'm going to begin by factoring the numerator and the denominator and seeing if there are any common factors that cancel. I recognize below that that's a difference of squares, and so the factor for that is going to be x plus 4, x minus 4. And the one above is going to be x minus 4, x plus 3. I notice that I can cancel the common factor x minus 4, and that is going to leave me with the simplified rational expression x plus 3 over x plus 4. So the domain for this is going to be all real numbers. And let's look at what the restraints are that we need to put. It's not all real numbers. There's a few numbers that would make the original expression undefined. If I were to put in x equals 4 or negative 4, then I would get 0 in the denominator, creating an undefined expression. So I exclude those values of x from my denominator. Because the x minus 4 term canceled, that's going to create a hole in my graph. And there will be an asymptote where x plus 4 equals 0, and that occurs when x equals negative 4. Let's look at part B. There's nothing to simplify on top. It's just one factor. And then down below, I can take out a common factor of x, which leaves me with, 1 minus x. Okay, so the only thing I can simplify here is that this x and this x, which leaves me with the simplified expression of negative 7 over 1 minus x. So let's talk about the domain. We begin with all real numbers, and then let's think about which values of x must be excluded. So looking at my original expression, the values of x that would put 0 in the denominator, making the expression undefined, are x equals 0 and x equals 1. So I'm going to exclude those from my domain by saying those are the values of x that we are not allowed to plug in. And now let's determine where there are holes in the graph of this function. This x term canceled out, and so it has disappeared from my simplified version. It would still cause a hole in the graph because it would create an undefined point in the original expression. It would give us 0 in the denominator. So there is a hole at x equals 0, and there's an asymptote at x equals 1, which again we get by looking at the simplified version and seeing that plugging in 1 to the simplified version would give us an undefined expression. So that's where there is an asymptote. Okay, let's look at number 2. So as we look at this expression, we're reminded that in this situation we are raising a power to a power. And so let's start by dealing with this negative 4 that's outside of the parentheses. So we've talked about the fact that this is not the distributive property really, but sometimes it helps people to think of it like that. And so let me just continue this line so we can see our expression. So I've raised negative 3 to the negative 4th power there, 4 to the negative 4th power there, and then down below we have p to the negative 2nd times the negative 4th power. Let's continue simplifying. So So at this point we're not done because we see p as a base has appeared twice, and we also have a negative exponent, and those are two things that we want to eliminate to have our expression in the most simplified form. So combining the base of p, I remember that p to the negative 16th means p to the 16th in the denominator. And so when I put those together, I am now left with 2m to the 12th over p to the 24th. And that is as much as we can simplify it. Let's look at the homework that you were assigned last night. We began speaking about number 18 in the last video, but it got cut off. We discussed how it does not simplify. The domain is all numbers as long as x is not equal to 0, and there is an asymptote at x equals 0. Numbers 17 and 19 are not worked out here because you have access to the answers in the back of your book. Number 20 is factorable, and it simplifies to x plus 2 over x plus 3. And here's the answers for that one. Number 22, again, taking a moment to just check your answers, and after you've looked at your answers, we will have an opportunity to ask questions about any that you disagree with or don't understand. You may have questions about the odd numbers too, and that's fine. And then let's look at this one. Again, we can pause the video if we need to spend a little more time on any of these. So let's talk a little bit about number 30, because that is different than some that we have discussed. When we are looking at a domain like this, we are just faced with the problem of determining where the denominator will be equal to 0, because this gives us the undefined expressions. X squared plus 4 equals 0 when x squared equals negative 4, right? Which I get by subtracting 4 from both sides of the equation. And though it's been a while since we discussed these kinds of problems, I remember that I can take the square root of both sides to get my answer. But let's see. X squared, that does not equal negative 4. So I think there is a mistake with that one. Let's put a big question mark by that one, and we will come back to it. So continuing, let's check our answers on number 32. Okay, and now we're going to begin our next section, which is learning how to multiply and divide rational expressions. We will take that on in the next video. Okay, before we move on, let's briefly revisit number 30. It's not factorable in the bottom, so though I can factor the numerator, there is no common factors that can cancel out. So for this one, the domain is all real numbers, all numbers, and there are no wholes and no asymptotes. And this is validated by looking at the graph of it in the region below. Okay, this concludes the first video of multiplying and dividing rationals.